Okay, so here go some responses to discussion questions that we are doing. So they start on page 352, and what I'd like you to do is discuss with another human. It's always good to bounce ideas off somebody else. And then for your homework, please write one sentence or draw a labeled diagram for each question. These questions are part of your homework assignment. And then you can do this, what you're doing right now, listen to the video lesson. And there are some, I will be drawing and that kind of audio. So, question number one, what is the evidence that sound travels as a wave? So, we have a couple things to talk about. Sound traveling as a wave. So first of all, we talked about waves as something that transports energy without transporting matter. And if you think about sound waves, so you're sitting here listening to a computer or whatever, and the fact that your eardrums are moving back and forth, meaning there's some energy used up in doing that, and that is provided by the sound waves, yet there's not a bunch of matter colliding with your eardrums, meaning wind. So imagine somebody talking, and they're, well, yeah. Okay, so they're talking and you are over here listening. Here's your ear. And what you hear is a bunch of wind going by, you know? They're talking and it sounds like you're sticking your head outside of a car moving fast or something like that. That's not the situation. If you're very close and whispering in somebody's ear, you can actually hear, you can feel, the wind of their breath on your ear. But when you're way out here, these air molecules stay where they are. They do not move all the way out to the person's ear. All right, number three. So children sometimes play with homemade telephone like this. So we have one of these in class, and it actually works. It's pretty impressive. If you remember Liam Kerrigan from a couple years ago, he built it. And it works. So the person talks and these air molecules move back and forth, and this end of the cup acts as a diaphragm, which is sort of like a speaker or microphone. So in this case, on this side, it would be acting as a microphone. It moves back and forth, and what that does is it sends vibrations, these would be longitudinal, through the string, and so the string moves back and forth, and it moves back and forth. And then this end would be acting as a speaker. So this moves back and forth as a diaphragm, and it moves these air molecules. So the air molecules vibrate and vibrate and vibrate, and it moves your eardrum, and you say, oh wow, I can hear what they're saying. So make sure you check that out in class. Yeah, it works. Question 4, when a sound wave passes from air into water, do you expect the frequency or wavelength to change? So we have a couple questions related to this, and let me draw a little diagram. Here's some water, so we have air above and water below. So here's what happens is, let's say there's a sound wave and it's loud, it's going this way, and what happens is the air molecules are going to move slightly, the water molecules, and the sound will be transmitted. We know that sound travels faster through water. So this is fast, and this is slow, quote-unquote slow, 343 meters per second. And so what happens is, so it sort of bend like this, and then whoosh. And so because the sound waves are traveling faster, the frequency is going to remain the same. Like this wave moves these water molecules, and these air molecules move these water molecules, and these air molecules move these water molecules. When waves pass from one medium into another, the frequency stays the same. Wavelength, however, is going to change because they speed up, and also because they bend like this. So not only does the wavelength change and the speed changes, but the direction changes as well. Yeah, okay. And I think we'll get to talk about diffraction and refraction, but yeah, that's an example of refraction. the changing of direction. So we expect the frequency to stay the same and the wavelength to change, and it would increase because it goes faster in water. 5. What evidence can you give that the speed of sound in air does not depend significantly on frequency? So speed of sound, it depends on a bunch of things: temperature of air, the density of air, our elevation. But imagine, so here we are again talking. I won't draw teeth in this person, and listening. Okay, that's pretty funny. So imagine that this person's talking, and when I'm talking, I'm emitting a variety of frequencies, right? I have some high frequencies and some low frequencies in my inflection or whatever. And so this person's speaking normal sentences, right? But imagine if the high frequencies went faster and the low frequencies went slower. This person would hear a sentence, but it would be all garbled, where the high stuff hit their ear first and the low stuff hit their ear second, and there'd be all this lag. And I think the sounds would be completely unintelligible unless you had a monotone voice, and then maybe people could understand you. And let's see, what's this? I think this is a video. Let's watch.
In unusual situations,
you don't always get what you expect.
Ah, that's
but
right.
Sometimes.
So that was Morgan Freeman, and he was inhaling helium. So I don't recommend that. It's probably not good for you, killing some brain cells or whatever. But whatever, he's made his millions. So question 6. The voice of a person who's inhaled helium sounds very high-pitched. Why? So there was Morgan sounding very high-pitched. And let's use this diagram here since it's already built. So here's an anatomy lesson. So we have vocal cords in here. And so the vocal cords sort of act as a resonating chamber. And they're fixed. Okay, the person as they talk, it's not like their neck changes length. That would be pretty weird. But so because that's fixed, and we consider this velocity is frequency times wavelength, when the person inhales helium, all of a sudden they have a bunch of helium gas in here, and that's very light, and so the speed of sound increases dramatically. It's almost 3 times that of normal air. But because the wavelength stays constant, what it means is the frequency has to increase to adjust. So you inhale pure helium and you talk, the frequency of your voice actually increases about by a factor of 3, which is something close to 1.5 octaves. And remember, an octave is double the frequency. So that, should we watch Morgan again? Nah, you could reverse and watch him again. But anyway, so there it is. Not recommending you do that. Okay, question 8. Explain how a tube might be used as a filter to reduce the amplitude of certain frequency ranges, and examples of car muffler. So the car is going to, here's the engine, car, and it goes through, there's this catalytic converter if you look under your car, or this box, and sometimes, well, no, the catalytic converter is small, so the box is probably the muffler as well. Oh, right, and the sound goes back and forth and back and forth. And then there's this tube, and it comes out the end, the exhaust. So this serves one purpose, and that is to get the exhaust from the engine not blowing out through the engine compartment and into the car, but out the back of the car, but also to reduce the sound. And so I remember I had a friend who had this Ford Mustang, and he had this tuned exhaust pipe, and it made these really deep, cool sounding exhaust sounds. But the idea is that there are certain frequencies and that the engine will emit, and so you can create a muffler that has certain dimensions, so certain frequencies would resonate. So we talk about something like this, an open tube, and we have a sound wave. So a specific frequency is going to resonate in the tube, which means other frequencies aren't and will cancel out. So based on the fact that you know if sounds of a certain frequency are going to come out, you could create a tube that does not resonate at those frequencies, so they would be canceled out and it would act as a muffler, muffling the sound. Question 9, why are there frets? Why are the frets? So these are the frets, and you push down on the strings and it changes the frequency of sound from the vibrating string. Why are the frets on the guitar spaced closer together as you move up the fingerboard towards the bridge? So this is a pretty accurate diagram of what a guitar would look like. And the idea is that musical notes, and I wanted to, but I A, B, C, D, E, F, G. So here's the musical scale. So I remember a little bit. I did take music theory classes, but if we go, and then next would be A. So from here to here, this would be 1 octave, or doubling the frequency. So 1, 2, 3, 4, 5, wait, I can't count. 1, 2, 3, 4, 5, 6, 7. All right. So if we look at between here and here, about halfway is 1, 2, 3, 4, 5, 6, 7. So something like this. Let's see how accurate this looks. So that looks like about, well, okay, it looks like about halfway. And the idea is that by moving 1 fret in, you're changing the musical note, okay, by some fraction. So let's say, hey, that was not a 3, that was a 7. So let's say, in going from here to here, we're reducing the frequency by 1/7, and then reducing by 1/7, and then reducing by 1/7. So if you're reducing by a certain fraction as the actual distance decreases, 1/7 of that distance thus decreases. So 1/7 of the total value gets smaller as we get closer and closer in to the bridge, and the length of the resonating string decreases. Alright, so that was a lot of words, but remember, we get this standing wave set up like that. This is exaggerated, where the string moves back and forth. And so if we were to hold, let's say we hold our finger right here, the length of the string is now reduced, and so the standing wave would look like that. So we have a shorter wavelength, which refers to a higher frequency. So again, if the wavelength decreases, the frequency has to increase, because the speed of the wave in the string depends only on the tension and the mass density. So by putting your finger on the fret, you don't change the actual speed of waves in the string. Alright, I think we can get through a couple more before you're bored to death. Let's see. No, we're going to stop. Okay, tune in for the next part. Thanks.